Welcome back to ECE 501B. We are 2 weeks left in the semester, but they are full weeks for us since we meet on Monday and Wednesday. We have 4 lectures. We will probably finish up chapters 8, 9, and 10 in this week, and then we'll finish all of the second textbook in the last week. That's the plan. We may not get all the way through the second textbook, but that's the idea. The idea would be you would be able to continue to work your way through that material. Today we will probably cover Chapter 8, but the analogous material in Chapter 9 is up to you, and that's the real material, the complex material, and that is not necessarily the complexity of the material. It's probably the complex material is cleaner to present than the real material. But that's our goal for today, is to cover at least Chapter 8, and I'm going to assume that you can then read Chapter 9, and then we will start in Chapter 10. But before we get there, some deadlines. Your last homework assignment is due in a week. That's the 7th. The deliverables 2 and 3, your project report is deliverable number 2, your reflective paragraph is deliverable number 3. Those are due a week from Wednesday. Teacher course evaluations, I assume you are getting emails if you haven't yet responded. Those are anonymous. I don't know who says what, and I don't see them until after grades are submitted, so you don't have to worry about me seeing your comments prior to posting grades. Either that's a good thing or a bad thing, but you can't butter me up with the comments. But I do use those to improve the class moving forward for the next semester. Obviously, I can't use them to improve the class this semester since I don't see them until sometime in July or July. Hopefully I see them before July. January or February is probably when I will see those. But those I would really appreciate you filling those out and giving me your feedback and input on what worked and how to modify, or what seemed to work for you, what worked well, what you think could be done differently. Our final exam is 2 weeks from tomorrow. It's on a Tuesday, and it's later in the day. It's from 6 to 8 p.m. Make sure that you have that cleared on your calendar if you're used to coming to campus on Mondays and Wednesdays. Well, in 2 weeks, you need to make sure that you have a Tuesday open on your schedule for the final exam. We now want to get into chapters, and Chapter 7, the last material there, is on D2L. I recorded that the day before the break, and if you haven't watched that, please look at those. There's actually 2 pieces to that. They're not both 75 minutes. One is maybe an hour, and one's maybe a little bit less than that. But those are dealing with singular value decomposition, or actually completing a proof and then getting into singular value decomposition. And singular value decomposition is very important, and we will use it, I think, in Chapter 10 when we start talking about pseudo-inverses. But after we get through Chapter 10, which I hope to do at the end of this week, we will get into the second textbook, which is online and in the resources section on the content page. Today we'll talk about generalized eigenvectors, and we may need these because we have seen that when we have a complex vector space, if we have normal operators, then we can diagonalize that matrix. If we have real vector spaces and the operator is self-adjoint, then we can diagonalize it. When we don't have normal or self-adjoint for complex or real respectively, then what do? Well, then we have to come in and introduce some generalized eigenvectors, and that's where we will start today. We'll define the characteristic polynomial of a matrix, and then we will talk about the Cayley-Hamilton theorem. And those are all matrix concepts if you've had a previous linear algebra course. And the main things in Chapter 10 that we will talk about are the trace, which in a nutshell, that's just summing the diagonal entries, and the determinant, and that's just forming the product of the eigenvalues. But we will talk about those a little bit more general than that, because those definitions we could simply state in one sentence and go home. So we'll do a little bit more than that in Chapter 10. Chapter 8, then, we are dealing with this notion of generalized eigenvectors, and the basic idea is that when we have self-adjoint, and obviously when we have complex vector space, we can loosen that up to only being normal. But with self-adjoint operators, we know that the eigenvectors form this orthonormal basis. But we don't necessarily always have that. And that's what we want to talk about now. In the complex spaces, this idea of self-adjoint, an SA, can be relaxed. And a normal operator just means that the operator and its adjoint commute, or we have these norm relationships. There's two ways of sort of thinking about what this normal operator looks like in a complex space. We don't need it to be self-adjoint. But now what we want to do, and this is really equivalent, so before we move away from these spectral theorems, the spectral theorems really are equivalent to saying that our vector space V has a direct sum decomposition of eigenvectors, essentially. But we can make that look a little bit more general by looking at this direct sum in terms of null spaces, and we know what the null spaces are, how they arise. Those are the operator minus the eigenvalue scaling a particular identity operator. So these spectral theorems are equivalent to saying that the vector space V has a direct sum decomposition in terms of 1D invariant subspaces. Those are the eigenvectors. And we could write that as saying, okay, V is U1, direct summed with U2, direct summed with U sub n. Or we could now define U1 through U sub n a little bit more specifically by saying that's U1 is really the null space of this operator T minus lambda 1I. The vector in that null space is forming this subspace U1. We can then direct sum decomposition that with T minus lambda sub 2I. That's where our eigenvectors are coming from. They live in the null space of T minus lambda sub I, and that's where these U1 through U sub m or U sub n are coming from. That's really all that's saying. When you see that large expression, all that's saying is these are just eigenvectors, the span of these eigenvectors, and they are all orthogonal, so that gives us this direct sum decomposition. If we're starting with self-adjoint or normal operators in real and complex vector spaces, we're assuming then that these lambdas are distinct. And that gives us this orthogonality of eigenvectors. What we have to worry about, though, is the real world is not always made up of self-adjoint and normal operators, and that's why we're working into or working through the material in chapters 8 and 9. Meaning, but what about non-self-adjoint, or in the case of complex, or non-normal operators? And if we're living in non-self-adjoint or with non-normal operators, then we may not have enough eigenvectors. May have an insufficient number of eigenvectors, which means that we can't necessarily decompose into one-dimensional subspaces, can't decompose in this one-dimensional subspace way, in this one-dimensional direct sum decomposition way. And if that's the case, then we may not be able to have these pure diagonal operators in this basis. Diagonal matrix may not exist. That's what we are now faced with when we have these non-self-adjoint or non-normal operators in the real or complex setting. The nice thing, though, is we can create some additional eigenvectors by simply enlarging our null spaces. And we can enlarge our null spaces by raising t minus lambda sub I to higher and higher powers. So we can decompose this vector space V as the null space of t minus lambda sub 1I raised to the n, direct summed with the null space of t minus lambda sub 2I raised to the n. N is the dimension of our vector space V, plus dot 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 plus, and now we may not have Nevada or little n distinct eigenvalues. Now we are assuming that we only have Michigan distinct eigenvalues, and so now we have to hope that some of these null spaces enlarge beyond just one dimension, so that we have multiple vectors in these subspaces. Here we are assuming that M is less than, Michigan is less than or equal to Nevada, and n is the dimension of our underlying vector space capital V. And we will introduce or need another piece of notation, which I'm calling little d sub I, and that's going to be the dimension of these null spaces above, for little I being associated with the distinct eigenvalues lambda 1 through lambda sub n. So the subscript I goes from 1 up to m, or Michigan. D sub I is the dimension of the null space of t minus lambda sub I to the n. And d sub I might just say, is the multiplicity of the eigenvalue, or that's the dimension of this null space. The dimension of that null space is the multiplicity of our eigenvalues. So now we are suggesting that we may have to enlarge these null spaces because now we don't have M may not be as big as N. And we hope then that we can find some additional vectors that lie in the null space, or these null spaces are larger than just one-dimensional. And that's what leads us to this concept of what we are calling now generalized eigenvectors. Suppose now we are given a linear operator T on a vector space V, and lambda, let that represent an eigenvalue of this linear operator. Then a vector, let's say little v, in our vector space capital V, we will call it is a generalized eigenvector of our operator T if T minus lambda sub I raised to the I, or I'm sorry, let me raise it to the jth, V is equal to 0 for some non-zero j. So here we're assuming that j is greater than or equal to 1. From that statement, though, I hope it's clear what that reduces to. If j is equal to 1, if we now have t minus lambda iv equaling 0, and we find a v that satisfies that, what were we calling that before? That was just an eigenvector. So the eigenvectors are generalized eigenvectors. It's just now we're enlarging that class in case we don't have n distinct eigenvalues associated with our linear operator. So our eigenvectors that we've been talking about all along are contained in this collection of what we are now calling generalized eigenvectors. Let's look at an example. And this is coming from the second edition of Axler, page 165. And that says we now have a linear operator T, and it's operating on a vector in 3 space. Z1, Z2, Z3 are the coordinates, and let's say that that linear map takes us to Z2, 0, Z sub 3. And at this point in the semester, you should immediately know what the eigenvalues of that are. Maybe not, I'm just kind of teasing, but you know from the eigenvalue-eigenvector relationship says that Tz equal lambda z, where z is now an eigenvector, and lambda is an eigenvalue. If that's the case, then on the left-hand side, that T of z is just the first right-hand side, so this now says that z2, 0, z sub 3 is supposed to be equal to a lambda scaling of the original vector z1, z2, z3. So this is now lambda z1, lambda z sub 2, lambda z sub 3. That's our eigenvalue-eigenvector relationship for this linear map T. And from this, now it's maybe a little bit easier to see what the eigenvalues might be. Here we can simply equate components in our two sides of that vector. We see that looking at the first component, we see that z sub 2 is equal to lambda z sub 1. And if that's true for all values of z1 and z2, what does that force lambda to equal? It has to be 0, doesn't it? If this is true for all z2 and z1. So now this is saying that lambda is equal to 0 if true for all z1 and z2. Now that may be easier to see once we look at the second equation. The second equation says that the second component, 0, is equal to lambda z sub 2. If this is true for all z2, then we definitely know that lambda is equal to 0. And now, what about the third component? z3 is equal to lambda z sub 3, and that implies lambda is equal to 1. So now we have these three eigenvalues for this third-order linear operator. And we want to find the eigenvectors. Notice we do not have three distinct eigenvalues. We have lambda equals 0 repeated. Our eigenvalues are 0 and 1. Let's look at the eigenvectors of the matrix representation of T. This you should be able to quickly write down by inspection from this definition. The matrix representation now from this linear operator T, the matrix, what's in the first row? It's now effectively some combination of z1, z2, z3 that just pulls off the second component or second coordinate of z1, z2, z3. Meaning the top row of A better just be 0, 1, 0. Then the second coordinate, after operating on it by this matrix, needs to just give you 0. And if we weight all of those components with 0, we will obtain that. And the third coordinate needs to return z sub 3 when operated on by A, and that says that we now have A with this structure, which is the matrix representation of T. And in fact, this is already in what in a math class you might have heard is a Jordan form representation. This is now a Jordan form. It's upper triangular. The eigenvalues are on the diagonal, and in fact, it's block diagonal. One block is 1 by 1. We had an eigenvalue at 1, but we had repeated eigenvalues of 0, and those actually did not return two 1 by 1 dimensional entries on the diagonal of that matrix. It now is forcing us to have this 1 in the off diagonal. Now, what happens when we look for the eigenvector associated with lambda equals 0? We're now looking for eigenvalues associated with A minus lambda I. With lambda equal to 0, this is just A, the original A matrix. Since we're subtracting nothing from that, and we want to know what vector, z1, z2, z3, lives in the null space of that matrix. And from this, we can just look at the three equations that result. This is three equations and three unknowns from the first row. We can see that the first row forces z sub 2 to equal 0. From the third row, the second row doesn't force anything, does it? z1, z2, z3 could be anything and still satisfy the second component. From the third row, now we're seeing that z sub 3 is equal to 0, which now says that since the second row didn't impose any constraint, z1 in this equation can be anything, and so now our eigenvector associated with the eigenvalue lambda equals 0 is 1, 0, 0, just to, let's say, normalize it to a length of 1. There's an eigenvector. What about for lambda equal to 1? Now we want a minus lambda I with lambda equal to 1. So we're now subtracting 1s on the diagonal from our original A matrix. And our original A matrix was 1 minus 1 in the 3, 3 entry, so let me just get rid of those and say that's now our matrix A minus lambda I with lambda equal to 1. And we want to know what vector or vectors might live in that null space. Or we are now looking at what combinations of z1, z2, z3 will satisfy this. From the first row, we see that minus z1 plus z sub 2 is equal to 0, or that z1 is equal to z sub 2. The second row says that minus z sub 2 is equal to 0. And those two in combination say that the first two components of our eigenvector both need to be identically 0, but we don't have any restraint on z sub 3. We have a complete zeroed column in that matrix A minus lambda I. Z3 can be anything, and so now we can say that the eigenvector associated with lambda equal to 1 is 0, 0, 1. And are we finished? How many eigenvectors have we found for this linear operator? 2. What's the dimension of this linear operator? 3. So we're missing an eigenvector, and we need to somehow find another eigenvector. We had 2 eigenvalues at lambda equals 0, so we need to find another eigenvector associated with that repeated eigenvalue at 0. Or what about the other eigenvalue at lambda equals 0? Do you see if in our original A matrix, if this 1 was actually a 0, do you see how that would translate into having a bigger null space when we replaced lambda with lambda equal to 0? Then the first row would give us anything for z1, z2, and z3, and the only constraint would be from the third row with z3 equal to 0. So we could have had a two-dimensional subspace in that null space if that off-diagonal term wasn't a 1 or was a 0. But that wasn't the case. Because that 1 was sitting there, now we have a Jordan form and we have to do something a little bit different. Lambda equal to 0 was a repeated root. And what we learned for this particular structure of the linear operator, there was only one eigenvector associated with lambda equal to 0. Or the dimension of the null space of A minus, let me just plug in the eigenvalue, which was 0, 0i raised to the first power, the dimension of that was 1. Which now says that we actually do need to introduce this new concept that we presented at the first of the lecture, and that is this concept of a generalized eigenvector. We need a generalized eigenvector to create a basis for our vector space V, which was in F3. So for a basis, what do we need? We need two things, don't we, for a basis? The vectors have to be linearly independent, and they have to span the entire space. And right now, we do have linear independence of 2, but 2 do not fill up a three-dimensional space. So let's now examine what we said we could look at when we're talking about generalized eigenvectors. Let's examine the null space of A minus lambda I, where lambda is equal to 0 squared. There's A, and if we repeat it, then in this matrix product, what's the first row? It's just pulling off the second row in that second matrix. That's what the top row of the left-hand matrix is telling us, and that's all zeros. The middle row is just all zeros because it's combining all three rows with weights of 0. And the last row says weight the last row in the right-hand matrix with a value of 1. And that leaves us then with this new matrix that only has a non-zero entry of 1 in the 3-3 entry of that 3x3 matrix. And we now are interested in the null space of this matrix. And I think it's clear that Z1, Z2 can be anything in our underlying field, and that's now the subspace that is in the null space of that matrix. We now have a two-dimensional subspace containing the generalized eigenvectors for lambda equal to 0. And we could actually write that then as z1 comma 0, 0, with z1 being anything in our field direct summed with 0, z sub 2, 0, with z sub 2 anything in our field. And that could then be two independent vectors. If we normalized those z's to be 1s, then those are orthonormal, and we now have an orthonormal basis for that operator that we started with of t. So that our full space F3 can be thought of as a two-dimensional subspace associated with the eigenvalue 0 direct summed with the one-dimensional subspace associated with the eigenvalue lambda equal to 1. That's from our example, but we can look at this maybe in a more general sense. Note that if t minus lambda sub I, let's say to the j, v is equal to 0, what can we say about t minus lambda sub I to the j plus 1 v? Now, if you look at the top equation, and all the bottom is saying is, oh, what happens when I pre-multiply by t minus lambda I? Well, now you're multiplying that by the 0 vector, so this better be 0. And that really just says then that all generalized eigenvectors are solutions of t minus lambda I to the n v equaling 0. which in our example, if we looked at t minus lambda I, which we were saying the matrix A minus lambda I, if we now raise this matrix or multiplied that matrix by A again on the left or right, do you see that we would just get that matrix back and we're not expanding on the subspace or the vectors in the subspace of that matrix? And that's all we're saying here is we can look at all the vectors in the null space of t minus lambda I to the n, and those will then form our generalized eigenvectors for that specific eigenvalue lambda. When we are dealing with complex fields, what do we know about what we can do with any of the linear operators t? We can put any operator t in this complex field into what kind of structure? Can we find a basis that's a little nicer than just every element in our linear operator being full or populated with some non-zero value? What was the result when we had any linear operator t on this complex field? What can we do with that, or can we find a basis that will make this operator a little nicer? And by nice, we're usually saying, can we put some zeros in there? Do you remember what that zero meant in this case? You remember what UT means? Not at Austin. But this is now upper triangular. So this is now, remember, for any operator t over this complex field, we can put it into an upper triangular representation or into an upper triangular form. And what do we know once we have it in that basis? Where can we find the eigenvalues? Those are on the diagonal. But typically that upper triangular form is not unique. We could find a lot of different bases that would put this operator into upper triangular form. Usually not a unique upper triangular form, and it's only diagonal. The matrix representation is only a diagonal representation if if we have enough of our normal or non-generalized eigenvectors. So I'll just call them regular eigenvectors. But what we're saying today is that we may not, when we're living in the real world, we may not always have a diagonal or a basis that makes our operators diagonal. And that is really saying, in general, the eigenvalues might be repeated. Let's say that each lambda is repeated a number of times equal to the multiplicity of that eigenvalue. So I'll just say equal to its multiplicity. And that multiplicity I'm calling d sub I, where d sub I is now the dimension of the null space of t minus lambda sub I to the n, where I is now ranging over m of the distinct eigenvalues of a linear operator. As an example, suppose we let the matrix representation of a linear operator T be 5, 1, 0, 5. I hope it's clear that this is upper triangular. And if that's the case, then what can you tell me about the eigenvalues? I have a repeated eigenvalue, and it's at 5. So lambda equal to 5 is an eigenvalue, and it has a multiplicity of 2. And if we wanted to check this, then we would look at t minus 5i, or if we now subtract 5 from the diagonal of our original, maybe I should say the matrix of t minus 5i, this now becomes 0, 1, 0, 0. What's an eigenvector for that? Or what's a vector that's in the null space of t minus 5i? And I could have 20 different correct answers if I'm not asking you to normalize it, right? What do you need to produce a vector in the null space of that matrix? What can you say about the components? Can you say anything about component 1 in the eigenvector? So now if I say, okay, here's the eigenvector, what can you tell me? Well, I didn't want those to be zeros. I just was trying to emphasize what's in this component and what's in that component. So now we could put anything we want here, couldn't we? But this guy has to be a 0. And if we want to make it a normal, or to normalize that, we might make it cleaner by saying, okay, here's an eigenvector 1, 0 that has a norm, a Euclidean norm of 1. What if we look at t minus 5i squared? So now take that earlier matrix, 0, 1, 0, 0, and multiply it by itself. I'll do the hard multiplication, meaning the bottom is just going to weight both rows with 0, so I know that's 0, but what's the top row of t minus 5i squared going to do? It's just going to copy the second row of that 0, 1, 0, 0, and the second row is just that. Now, what's the subspace that lives in this null space? So what vector or vectors, when scaled by this matrix, will give you the 0 vector? Everything. So now this is all of R2, or let's just keep it in the reals. All of R2 will satisfy this. Well, we've already found one. We found the eigenvector for lambda equal 5, but we couldn't find anything else that's not independent of E1. So we had to then look at these generalized eigenvectors. Now we've opened up anything we want. So the cleanest might be to just say, well, let's pick one of those to be the x-axis, so to speak. Let's just say, okay, we can make that vector be true. And if that's true, then we could pick pretty much anything we wanted as long as the second component of that vector was non-zero, and it would be independent of E1. The cleanest might be to just make it orthogonal and normalize, so now we have E1 and E2 as generalized eigenvectors for that original map that had a matrix representation of 5, 1, 0, 5. And if I ask you to find what is T, do you see what that would be? What would the first component be? Is that clear? So that we are comfortable with doing this on the final exam. I could give you a linear operator, and now you need to find its matrix representation. Oh, now I see very clearly that I have an upper triangular matrix. The eigenvalues are on the diagonal. They're repeated, so I may have to worry about, and now that I have that non-zero off diagonal, this is not a purely diagonal matrix, I'm probably going to have generalized eigenvectors, and here they are. So in this example, we found that the dimension of the null space of T minus lambda I squared with lambda equal to 5 was 2, and that was actually spanned by E1 and E2, where E1 is in fact a true eigenvector that we have been dealing with all along since, what, chapter 5? Is that when we started talking about eigenvectors? That won't be on the exam as far as which chapter this material is in, but you need to know it. And E2 was introduced by expanding this collection of vectors in a null space by raising T minus lambda I to a higher power, and this is now E sub 2 is a generalized eigenvector. And what you will find is that if you sum all of these multiplicities, that's going to give you a number that equals the dimension of our underlying vector space V. That's generalized eigenvectors. You can create those, and now let's look at some other concepts. Let's look at a characteristic polynomial, and that will be defined. We will just define that to be this polynomial Q of Z equaling, now that we've defined multiplicities and we know what eigenvalues are, where the eigenvalues are lambda, let's assume we have M, or Michigan eigenvalues, and they have multiplicities D1, D2 up to D sub M. the characteristic polynomial is z minus lambda 1 to the d1 times z minus lambda sub 2 raised to its multiplicity, and we just keep multiplying these factors together of our appropriate eigenvalues with the corresponding multiplicity. And Q of Z is the characteristic polynomial. And where are those lambdas? Those lambdas are associated with some linear map. So this characteristic polynomial is associated with a given linear map, capital T. And I hope that it's obvious. Obviously, the roots of this characteristic polynomial, Q of Z, equal or are the eigenvalues of that linear map. There is the then characteristic polynomial. Now let's talk about another concept, the Cayley-Hamilton theorem. The Cayley-Hamilton theorem is stated as follows. Suppose we are now, and again, we're in chapter 8, this is 820, so we're given a complex vector space V. Given V a complex vector space, a linear map, a linear operator, which is more restrictive than a linear map. Now we're mapping from that vector space V back into itself, so we have an operator T. And now let's say that Q of Z is the characteristic polynomial of T, and we know how to build that. We find the eigenvalues of T, and their multiplicity, and we just produce this characteristic polynomial. That's what we defined before. But the Cayley-Hamilton theorem says that the linear operator actually satisfies that characteristic polynomial. Meaning if you plug T in everywhere that you see a Z in that characteristic polynomial equation, you will get the result equaling 0. And this is now a matrix equation, Q of T. Since we're trying to get through all of chapter 8, I'll let you see the text for that proof, and let's just look at an example. Suppose that we now have T on a three-dimensional space, again being Z2, 0, Z sub 3. And that should feel very familiar. The matrix representation of that linear map, if we call it A, is just 0, 1, 0, 0, 0, 0, 0, 0, 1. And since that's the matrix representation of A, you can immediately tell me what the eigenvalues are. Since it's upper triangular, A is, and the eigenvalues are on the diagonal, we have 0 repeated. It has multiplicity 2, and we have one eigenvalue at 1, and its multiplicity is 1. That now allows us to generate this characteristic polynomial. That's now Z minus lambda 1 times Z minus lambda 1, since it's doubled, or it has a multiplicity of 2, times Z minus 1. or that's z minus 0 squared times z minus 1, or z squared times z minus 1. And Cayley-Hamilton tells us what? That says that Q of t, which is t squared t minus, and now we have 1 times the identity matrix I, that's actually equal to 0. That's the Cayley-Hamilton theorem. And if we looked at the matrix representation of A, which is maybe easier to deal with, that now says that it also satisfies that characteristic polynomial, or a squared times a minus I is equal to 0, where a is this matrix representation of t. And it's not too hard to check, and it's kind of fun to do that. We've already generated some of this. We've already looked at a squared. A squared gives us everything as 0 except the 3, 3 entry, and that's 1. And a minus I gives us, whoops, I would have gotten a nice result, wouldn't I? A really nice result, which would have really made me start wondering what happened. So now there's a minus I, and if we look at Q of A, which is a squared times a minus I, the only potential non-zero entry would be in the last row. If the second matrix in that product had anything in the last row, then we would have something that was non-zero, since a squared is just saying zero out the top 2 rows and copy down the third row. Well, the third row is all zeros, and so we do get the 0 matrix for Q of A, which is what the Cayley-Hamilton theorem says will happen. Let's now look at something that's somewhat related. We're still in Chapter 8, Proposition 822. This says if we have a linear operator T on a vector space V, and some polynomial P on a field of numbers, and I haven't said what that needs to be, so this could be any polynomial over a field F. But now we know what it means to find a polynomial in terms of a matrix or an operator. We just plug in, this is now a polynomial, so we would just have T or its matrix representation as different powers of T or A. What we're saying in Proposition 822 is that the null space of P of T, and what I was trying to suggest is you know how to compute P of T. Just put T in everywhere where you might have a Z in this polynomial. The vectors in this null space are actually invariant under the original map T. So if you give me a polynomial, and then we find the null space of vectors, or I'm sorry, the vectors that live in the null space of that polynomial of t, those vectors, or that subspace, those vectors in the null space of P of t, those are invariant under our original linear map T, or our linear operator T. Let's look at where that comes from. Let's now pick a vector, any vector in the null space of P of t. So you give me a polynomial, I'll generate this P of t, that will just be a matrix, and I will find a vector in the null space of that matrix. If that's the case, what's that? How did we define V? V is supposed to be in the null space of this matrix, and P of t is the matrix. So we have this matrix post-multiplied by the vector V. This better be 0. That's by definition of V. Now we have this, and what are we trying to find? We're trying to say that if we start with V, and it's in the null space of P of t, then if we map V through t, that output vector better be in the null space of P of t. We want to see what that equals. So we're now taking V. Maybe I shouldn't have put that in parentheses. Maybe that's not consistent. So now we have TV, and we want this. TV is what? Well, this will be 0 eventually, but TV is just some mapping through t of a vector in the null space of P of t. But what I'm going to suggest is t, or I can rewrite this as t, P of TV. Why can I do that? I'm saying that P of t and t commute. That's all I've done. I've just interchanged t and P of t. I'll prove that, or I'll show that in a minute if you don't believe that. But what is this piece? By definition of V, that was 0, and now t, a linear operator on the 0 vector, gives us 0, and now the left-hand side equal to the right-hand side gives us what we want. Why do P of t and t commute? What is P of t? That's just a collection of t's raised to different powers, isn't it? It's a linear combination of t's in various powers. And what happens when you hit a power of t with t? It doesn't matter which order you do that in, does it? And the polynomial will just have scalars scaling those powers of t. And those scalars can slide through those powers of t and t. So P of t is just a linear combination powers of t. So that's justifying that or rationalizing that question. And this expression or equation shows that the vector v that lives in the null space of p of t is also living in the null space of p of t if we start with v in the null space of p of t. That actually now allows us to say a little bit more or generalize this concept of breaking down operators into nicer representations. This gives us a nice decomposition. And by nice decomposition, now you're learning what I mean by nice. That means there's zeros in a lot of places. That's what I'm meaning by nice. And that's now in the following theorem. This is theorems 823, 828, and corollary 825. So this is how you cover a chapter in a day, is you just combine all the different theorems and corollaries into one theorem. Here's what I want to do. For a vector space V that's a complex vector space, a linear operator T on that vector space, lambda 1, lambda 2, lambda sub m, the distinct eigenvalues of T with u1, u sub 2, up to u sub m, the corresponding invariant subspaces, and in fact, this is just sort of a side note. Well, we're trying to make it such that they're not necessarily one-dimensional. We may have M may not be the dimension or the size of the vector space V. And if we have generalized eigenvectors, then some of those subspaces, u sub 1 through u sub m, are more than just one-dimensional. Now let's see what the parts are to this theorem. A, there is a direct sum decomposition of the vector space V of the obvious form of the form V is equal to u1 direct summed with u sub 2 direct summed all the way up to u sub m. Each of these subspaces, u sub j, is invariant under the linear operator T, where u sub j is now the subspace containing the vectors in the null space of T minus lambda sub j I raised to the n, where n is the dimension of our vector space, and C, there exists a basis of our vector space V with respect to which T is not diagonal but block diagonal, meaning the matrix representation of T is now A1, A2, A sub m, where those blocks are dimensioned consistent with the subspace dimensions U1 through U sub m. And I'll just quickly say that those blocks, further, each block, the A1 through A sub m, is upper triangular with the form A sub j equaling, along the diagonal, what do you expect? Those are our eigenvalues, these lambda sub j's, and it's upper triangular, so we may have mess above the diagonal, but this is what we have for all of these j's in M. And if M was equal to N, these blocks, these upper triangular blocks, would be 1 by 1. And if we have generalized eigenvectors, then we may have bigger dimensions on these A sub j's. So this really concludes Chapter 8, and Chapter 9 is just the extension of these ideas to real vector spaces. And I'll maybe write that down at the end, but I'll let you go. Thank you for giving me an extra couple of minutes to get through Chapter 8.